So again, thanks for the introduction. Actually, I'm going to talk on when standard security, meaning CPA security, implies security against selective opening attacks. And this is actually joint work with Eike Kilz from Ruhr University Bochum as well, and Georg Fuchsbauer and Christoph Peterczak from IST Austria. So let's have a look at what selective opening attacks are. So we consider a bunch of senders on the right-hand side, sending messages to one common receiver sitting on the left-hand side, and well, all the parties hold the public key of the receiver, have messages they want to send to the receiver, and choose fresh randomness of their own, encrypt the messages, and send them to the receiver. And we not only consider an adversary that sees everything that is sent on the channel, but the adversary is allowed to corrupt an arbitrary number of senders. Right, so let's assume the adversary corrupted sender 1 and the last one. And the natural question to ask is whether the messages sent by non-corrupted parties, like sender 2, remains confidential. And actually, it's not even clear what confidential means, but we'll get to that in a minute. So to give you some background, this is a problem that naturally arises in multi-party computation, where you consider corruption of parties. The problem becomes interesting because messages may depend on another. That is, if an adversary corrupted sender 1 and learns message 1, this might already leak some information on message 2, and so on and so forth. Until recently, we had no idea if standard security does imply security against selective opening attacks, and only at the end of last year we had a nice negative result, assuming that we have some strong notion of obfuscation and correlation tractable hash functions. We can show that not even standard CCA security is strong enough to imply passive security against selective opening attacks. And actually, the problem itself is not really new. It was already introduced in a paper by Dwork in 1999, where it was considered for commitment schemes and later adopted to public key encryption schemes. So let's have a look at how we model security. So we allow the adversary to see the public key, and the adversary has control on the messages that are going to be encrypted. That is, he chooses a distribution and submits it to the game, somewhere on the left-hand side. And let's think of encrypting a message as in putting it in a box. Right? So we sample messages, encrypt all of the messages, put them all in a box, and the adversary is going to see all the encrypted messages. And right now, the adversary is allowed to do corruptions. And let's say the adversary corrupts message M2. And so far, this is not really interesting because there's no way for the adversary to verify that ciphertext 2 actually contained message M2. And we are going to reveal the randomness used to encrypt message M2 as well. And right now, the adversary can check whether C2 was actually encrypted using message M2 and randomness 2. And let's say the adversary corrupts ciphertext 1 and ciphertext N. And at some point, the adversary is done with its corruption phase. And as a challenge, we either send the adversary the sampled messages, or we resample messages that are as likely as the sampled messages, given the messages the adversary already knows. Okay, so we resample messages, and we fix the messages the adversary already saw, like M1, M2, and M5 to Mn. And only the messages the adversary didn't see so far are really resampled. Somewhat to model that revealing corrupting ciphertext already might have leaked some information on non-open ciphertext. Right, and ideally we would hope to have some computation indistinguishability between the sampled messages and the resampled messages. Make sense? Okay.
Is the resampling efficient?
We'll have to assume it. We'll hardwire it to the definition. So actually, there's two definitions. If you restrict the messages to the distribution of the message to be efficiently resamplable, it's called weak selective opening security. And if it's supposed to hold for arbitrary distributions, it's strong selective opening security. But so far, we have no instantiation of a strongly selective opening secure scheme. So we'll get to that in a minute. So he sees all the encryptions, then he's allowed to do corruptions, learns the messages and the randomness of corrupted ciphertexts, and then later on gets a challenge. Okay? Okay, so let's have a look at the actual security definition. So we generate a key pair of public key and secret key. The adversary sees the public key and chooses a distribution. and we sample messages. As seen before, we encrypt all the messages using fresh randomness and send the ciphertext to the adversary. And usually you would model the corruption phase adaptively, meaning the adversary makes an adaption query, learns message and randomness, does another one. But for simplicity, let's just assume the adversary chooses a subset of 1 to the n and learns all the messages and randomness at those positions in one shot. And after that, we do the resampling. That is, we sample messages from D again, conditioned on the messages the adversary already knows have to be the same as before. Okay, and then we, depending on the bit we fixed in the experiment, we either send sampled or resampled messages to the adversary, and he, well, gets a shot at guessing the bit. And ideally, we would like to have that no PPT adversary behave significantly different in either of the two games. Okay, and actually, some of this notion has already been around in 1999, and there has been no positive result for non-trivial distributions. And all that remains to argue is that we can bridge one of those transitions using CPI security. Okay, so let's have a closer look, and actually we're going to see why we can do that step from switching M4 and M5 from sample to resampled. Okay, what is going to happen? Well, so in general, you would have to guess all the opening queries in advance, to do the resampling in advance, to submit it to your TPA challenger, to learn the ciphertext, to embed them in your challenge. However, given the structure we have, we can simply guess an interval in this vector. And if you think of this as a graph, we would guess a connected subset of the nodes. So let's just say we guess the interval, because the reduction is not going to know that message M3, M6, and M8 to Mn will be opened. Right? So we simply guess. And exploiting that we have a Markov structure, that is only n square many such intervals. And we have a decent probability in guessing correct. Okay, let's say we just guess. And what we do in the next step is, well, we are just going to resample messages. And for resampling, we are going to fix message M3 and M6. Because the distribution of message M4 and M5 only depends on M3 and M6 due to the Markov property. And once we did that, we know, well, we already sampled those messages. We resampled essentially the whole vector, but all we need is the resampled version of M4 and M5. And we submit those two message vectors to our CPI challenger. Actually not a CPI challenger, but a vectorial CPI challenger, but it's equivalent. You can do another hybrid argument over every single message. Okay, and once you obtain the ciphertext, we can simply encrypt all the other messages, namely those fellas. Well, we will embed our challenge right here, and those messages on our own and send them to the adversary. There's only one downside, namely opening queries might still happen. And assuming that we guessed correctly in step 1, we can be sure that, first of all, the adversary is going to open message M3 and M6. And we can be sure that no opening query will happen within M3 and M6. If there's going to be an opening query in there, we simply guessed not correct, have to abort. But assuming that we guessed correctly, this is going to work out. And opening queries in this area here will not cause a problem because we will be allowed to return sampled messages anyway. So we don't have to care about opening queries because there's not going to happen any resampling. However, on the left-hand side of M3, potentially opening queries might happen which influence the distribution when resampling. And the nice property is that we can just wait for all opening queries on the complete vector to happen, and then do another resampling. And once we know all the opening queries, actually we don't have to care about opening queries on the right side of M3, but let's say there's some opening queries somewhere here. We resample messages again, and those messages up to M3 will have the correct distribution because we sampled conditioned on every opening query, in particular the opening query is relevant on this area. And we can just use that we revealed message that M3 is revealed and fixed to glue those partially resampled vectors together. That is, we can just take M1, M2 tilde, plug them in here. Then we have an opening query. And then we can reveal either this or this message vector. Actually, it doesn't make a difference because the CPL challenger will decide in which game we're actually in. And then we can just continue with the sampled messages. And the fun thing is, due to the Markov property, we can, well, just exploit that M3 got revealed and glue the partial vectors together. Right, and this is how you get the reduction to work. Yeah. So actually, this is an idea you can apply for Markov distributions. And we could extend it to graphs that have certain low dependency structures. Actually, our approach is limited due to the fact that we have to guess the interval. And if you consider graphs, you have to guess a connected subgraph. And, well, we have to have a decent probability in guessing the connected component correctly. And we're limited to graphs that have polynomially many connected subgraphs, which essentially applies to Markov distributions and variations thereof. However, there's still a gap to the distribution used by Hofheinz et al. In their impossibility result. The distributions considered in their paper stem from secret sharing. And well, there's still a gap from our positive result to their negative result. And actually, it might be interesting to see if we can extend our technique to go for more involved distributions or extend the negative result to simpler distributions. And actually, I would be happy to discuss any result on that or any ideas. And you can find the paper on ePrint, maybe have a look. And thanks for your attention.
Question? Can you repeat what's a Markov distribution? Can you repeat what's a Markov?
Sure. The distribution of some message mi only depends on message mi minus 1. Yeah. So once you know the predecessor, the distribution of message mi is given. It's not efficient. So actually, I glossed over that detail because it's somewhat technical. In the actual definition, you're restricted to efficiently resamplable distributions. This is hardwired to the definition.
So why isn't the distribution of these guys that puts the bound of this point?
There's too many dependencies. So it's, if you try to model a secret sharing distribution like T out of n, you would have two isolated nodes representing the first T messages, and from then on, every next message would be connected to all of the first T messages. And there's just too many dependencies in the graph.
Because you need the redundancy to keep the graph, right? The redundancy is more than expected.
I guess.
But isn't it efficiently resamplable, the secret sharing thing?
Yes, it is. Yeah.
Okay,
So
let's take this off.
the result by Hofheinz et al. Rules out that CCA security implies weak int selective opening CPA security.
Any more quick questions to Felix? Okay, so let's thank him again.